Hello friends, in this video we are going to discuss ordinary differential equations of second order that are homogeneous. Now we must appreciate that the second order ordinary differential equations are very important in the design of dynamic systems. For example, the design of resistor capacitor series circuit and maybe resistor inductor series circuit. They all involve utilization of second order differential equations. In this video, we are going to see how we can define them in Matlab and then go ahead and return a symbolic solution or a general solution of that second order differential equation. Now we are going to first of all create a script in Matlab which we are going to name it diff equation 2.m, and after saving that name, let's go ahead and write our script in Matlab. So the equation that we have in this example is the 2y dt squared plus 4y dt plus 4y is equal to 0. This shows that this function is equal to f of t, and f of t is equal to 0 becomes a homogeneous equation. If f of t is not equal to 0, then it becomes a non-homogeneous second order differential equation. So what we have here is a homogeneous ODE, and let's move ahead and see how we can define it. So we are going to say this is ODE, and is going to be defined by diff, it is y, is a derivative of y with respect to t, and is of order 2. Okay, let me write it like this. It's of order 2. Now we have to add 4 times diff of y with respect to t, we close, then plus 4 times y, and we are going to use the comparison operator, and we are saying when this the 2y dt squared plus 4 dy dt plus 4y is compared with 0, it should return true if it should return 1 if it is true and 0 if it is false. So we are proceeding, and we are going to first of all say the solution y sol is going to equal to, in other words, this is our solution. We are going to say d solve, because the available solver to return a symbolic solution of an ordinary differential equation is d solve, and our ordinary differential equation is ODE, d solve ODE. Let's run this and we see. Okay, let's first say clear our command window, then we go back and run this. So it produces the solution equal to C1 exponential negative 2 times t plus C2 times t times exponential of negative 2t. So this is our general solution, or the solution of the ordinary differential equation that is symbolic. If, for example, we want to change this C1 and the C2 to A and B, like, because Matlab uses the default C1, C2, C3 like that to mean constants after solution of the ordinary differential equation. Because remember, there is a integration of the differential equation, and so the integration comes with constants. So the first integration brings C1, the second integration brings C2, and let us see if we want to change the C1 to A and the C2 to B, how do we do that? So we are going to say maybe that is going to return y sol 1, which is equal to, we are going to substitute in y sol, okay, wherever we see C1 and C2, let's close. We are going to put there A, A, and B. Okay, so let's run this and we see what it produces. Okay, we can see, let's clear this, and maybe we suppress this one. So we can see where there was C1, it has now substituted it with A. Where there was C2, it has substituted with B. So let's go and now define the initial conditions. Let's define initial conditions. Okay. Okay. Let's define initial conditions. Initial conditions. And we say, first of all, condition 1. Condition 1 is equal to, we want to say at t equals 0, when it is equal to 0, then y should equal to maybe 1. Let's suppress that. Then condition 2, we say when y, when t is equal to 0, that dy dt should equal to maybe 2 or should equal to 1. So we are going to use the function substitute. We are going to substitute wherever there is a t, we substitute it equal to 0 in the first derivative of this function. So diff of y, in diff of y, wherever there is t, we put there 0. Okay, so if we say we substitute it with 0, it means in the first derivative at t is equal to 0, then it should equal to also some other value which we are saying maybe is equal to 2. Okay, so let's go ahead and maybe say our solution finally should equal to d solve. We have ODE, then condition 1, and condition 2. Okay, so let's run. Let's run this. Okay, when you run, you see, using now the initial conditions, our solution is exponential of negative 2t times 4 times t plus 1. Okay, so that is our final solution of the ordinary differential equation. We can maybe copy it here and put it in our script, and we know we have suppressed it in that manner. So this is equal to exponential of that. So we have finally gotten the solution for our ordinary differential equation. In the next video, we will see how we can add more parts, and then we'll be able to solve this numerically using some other Matlab functions. Thank you so much.